In the last video, we reviewed what an identity was. That's an equation that's always true if both sides are defined. Okay. In the next couple of videos, we're going to be working through what we call the fundamental trig identities. These are the ones that you want to have at your fingertips. You've either got them memorized or you're familiar enough with them that you're able to figure them out very, very quickly. Okay. So what I've done on the board here is I've just reminded us of the unit circle definitions of the 6 trig functions. So if this is my unit circle here and I've got an angle theta, the point where the terminal ray, when I draw it in standard position, intersects the unit circle has coordinates capital X, capital Y. And of course, by definition, capital Y is the sine of that angle and capital X is the cosine of that angle. Now, there are several identities that fall out directly from those definitions. So first of all, we've got the reciprocal identities, because we've got 6 trig functions and 3 of them are just the reciprocals of the others. So for example, I can say cosecant of theta is the reciprocal of sine of theta. That's actually the definition of cosecant. Okay, so that's always true whenever both sides are defined, and in this case, if the left side is undefined, so is the right side, because I can view this as a definition. This comes with the fact, though, that sine of theta is the reciprocal of cosecant of theta, and that's an identity, but it's not the definition of sine, because sine of theta is always defined, but the reciprocal of cosecant is not defined at any angle where the capital Y value is 0. So at these 2 points on the unit circle, which would correspond to multiples of pi, the right-hand side is undefined, but the left-hand side is defined. Okay. So some of the reciprocal identities are actually definitions. Secant and cosecant are defined as the reciprocals of cosine and sine. But the other reciprocal identities aren't the definitions of the trig functions, but they're always true whenever both sides are defined. Okay. So secant of theta is the reciprocal of cosine of theta, and that really, I can say that is the definition of secant, because secant is 1 over the capital X value, but by definition, the capital X value is cosine of theta. Okay. Cosine of theta is then the reciprocal of secant of theta, but again, if I'm at, in this case, an odd multiple of pi over 2, the right side will be undefined, but cosine is always defined. So this is the definition of secant. This is an identity that's true for cosine when secant is also defined. Okay. All right, and then I can say that cotangent of theta is the reciprocal of tangent of theta. And we discussed in the last video that this is true whenever both sides are defined, but that's not the definition of cotangent, because cotangent will be defined at odd multiples of pi over 2 where tangent is undefined. And similarly, tangent of theta is the reciprocal of cotangent of theta. Again, whenever both sides are defined. And again, that really follows from the definitions, because what's the reciprocal of y over x? X over y, provided, of course, that y isn't 0, so that's defined. Okay, so those are our reciprocal identities. Not a whole lot to learn here, because if you know the definitions, this follows directly from that. Okay. There are 2 other identities that follow pretty directly from these definitions, and those are our quotient identities. Tangent of theta, we can see that's y, capital Y over capital X. Well, that's sine theta over cosine theta. And again, that follows directly from these definitions. And then we've also got the cotangent of theta. And I sort of remember this by thinking, oh, that's the reciprocal of tangent, if they're both defined. This is then cosine of theta over sine of theta. That also follows directly from this definition, although I usually get it by just saying, oh, it's the reciprocal of the one for tangent. All right, now we'll eventually be working with these. I find these quotient identities helpful because sometimes I've got an expression that has a lot of trig functions in it. I can write every expression that has trig functions in it in terms of just sine and cosine, which are the 2 that I'm most familiar with. If I have secants, I just rewrite them as 1 over cosine. If I have tangents, I can rewrite them as sine over cosine. So these identities give me a way of writing everything in terms of just the two trig functions that I'm most familiar with. And that's often a strategy that we'll be using as we're trying to simplify some expressions and eventually to simplify so that we can solve some equations.